Okay, so in this video I'm going to work through the volume intro. This is a worksheet that you can find in the Canvas week 7 module. So it might be a good idea to just download it and print it off and have it ready to kind of follow along with, or you could try it and you could pause the video and try it ahead of me and then watch the video, or however you want to do it. But anyway, it's a tool for you to use. So this first part, we're going to kind of ease into it. It says let R be the region bounded by y equals x squared, y equals 1, and the y-axis. Okay, so if we draw a little picture of that, y equals x squared looks something like that. Y equals 1, be right about there, and the y-axis. So that means we're talking about this region inside here. So we got the y-axis is one of my borders, y equals 1 is another one of my borders, and x squared is the other border. So there's 3 borders there, and it finds a region. So if we wanted to find the area of that region, we know how to do this, right? You'd go, you could draw little rectangles to help you kind of come up with how to do this, but this would be the integral from 0 to 1, because we know this is 0, and we know that point right there would be 1, because that's where y equals 1 and x squared connect. So from 0 to 1 of, and my height would be 1 minus x squared. Y'all buy that? Because this is always 1, that's always x squared. So any rectangle that I'm going to draw is going to be between 1 and x squared. And I'm subtracting it because notice if we grab a different color here, like red, you can see that distance right there is the x squared, and get a different color like that. That distance right there would be the thing I'm looking for, and what other color? This total distance would be 1. So you can see that's why I'm taking 1 minus x squared to get the distance I want. Okay, let's get back to our normal color here. And so we put a dx in there. Oops, that's not another color. That's funny. Dx. There we go. Okay. And of course we could find that area by just integrating that. I'm not going to integrate all of these. I'm just going to set them up, but I'll integrate this first one just so you remember how to integrate. This would be x minus 1/3 x cubed evaluated from 0 to 1, and that would be 1 minus 1/3 minus 0, which would be 2/3. Okay, so now the next step is find the volume of the solid obtained by rotating R around the y-axis. Okay, so I'm having that same region, R, looks like this, and I'm going to rotate it around the y-axis. So you can see that there's going to be, looks like it'll be like the tip of a bullet kind of. And I'm going to break that into little discs. So as we talked about in class, these are little really short cylinders. Now the first question we want to figure out is, it's a cylinder, not a washer, so there's no hole in the middle. So it is a washer, which means I need to find the volume of a washer. I'm sorry, it is a disc or a cylinder. There's no hole in the middle. So if you think about volume of cylinders, the volume of cylinder is pi r squared times height. So in this little cylinder, the height is going to be a small little change in y. So there's a small little change in y, and that right there would be the radius. So if I want to find the volume of this thing, I'm just adding up a bunch of those little discs. So I'm going to integrate. I'm going to have a pi out here. I'm going to have my radius squared, and then I'm going to have my height. And notice that the height is just a little change in y, so that gives me a dy. Okay? So now I just got to figure out what the y is. I'm sorry, what the r is. Now, and I'm going to need to figure out my limits of integration. So now the r is, we drew a picture of it. Let's blow up that up a little bit. So if we erase all this other gunk, this has just helped me look at what the shape looks like. But what I really care about is what my r is. And you can see that the r is changing as we go through our y values, doesn't it? It's getting longer. And notice that the r is dependent upon my function. Okay, now, so we can see that it's changing. It's not just going to be a solid number. And we see that it's dependent on our function. We know that our function is y. Remember, it's y equals x squared. So this line here is y equals x squared. So now, this is really important. This can help you for the rest of the sheet. So what I'm going to do is pick one of these spots, like this one right here. Let's zoom in again. And I know that that point has an x coordinate and a y coordinate. So we could talk of that point as x comma y, just be as generic as we can. But because it's specific to a certain equation, we could actually write this as x comma x squared, because that's how y is related to x squared. But also, because of this relationship, I could also describe this point as the y value, in terms of the y value. So the y coordinate is y, which means the x coordinate is the square root of y. So these both, you could describe any one of the points on this curve using this guy or that guy. Now, why do I care about that? Well, because the points on the curve give me a certain distance. I know that this distance right here is the x coordinate, and that distance right there is the y coordinate. So if I care about those distances, all I need to know is what the coordinate of that point is. Okay? So let's go back here and see which one we care about. Get it small again. So we're looking for, remember, the radius, and the radius would be that red line, wouldn't it? Well, the red line is just the x coordinate. So I could call it x, or I could call it square root of y. It would be the same thing, because both of them are expressions for the x coordinate. Now, I choose square root of y because I already determined that I have to have a dy over here, and this variable has to match my dy. Okay, and why did we pick dy? Remember, because we saw that the disks are stacking up on top of each other, so the little bit of height of the disk is in the y direction, so that's why it's a change in y. And so that means this has to be in terms of y, and that also means that my limits have to be in terms of y. So I'm asking, so I look at this region and say, okay, what y's am I using? Well, I'm going from there up to there. This is y equals 0, that's y equals 1. So that means I'm going to go from 0 to 1. All right, so, and that would be 0 to 1 of just y, because square root of y squared is y, dy, so that would be pi over 2 times y to the squared over 0 to 1, and that would be, if I plug in a 1 and a 0 in there, I just get pi over 2. Okay? Now we're going to find the volume of the solid obtained by rotating r around the x-axis. So let's draw our picture again. We got this same region, but this time we're rotating it this way. So you can see there's going to be a little inner hole here, isn't there? It gets smaller as you go down. Because if we did a cross-sectional area, it would look something like this. So you can see there's a little hole in here. The outside is just going to be a big cylinder. Okay? So in this case, instead of having a disc, I'm going to have washers or donuts because there's a hole in the middle. So immediately I think of if you think about a disc, it looks like this, right? I'm sorry, if you think about a washer or a donut, it looks like that. And so notice this is just a cylinder with a smaller cylinder taken out of the middle of it. So the volume for this thing is going to be pi times some big R squared times height minus pi by some small r squared times height. And since they both have heights and both have pi's, we could say pi times big R squared minus little r squared times height. And that's the basic formula we're going to use anytime we're trying to find the volume using washers. So notice this up here. Where was it? This guy, I erased it, but this pi r squared times height, that's what we're going to use whenever we're using discs. This is what we're going to use whenever we're using washers. How do we know if we're using a disc or a washer? If there's a hole in the middle of our shape. How do we know if there's a hole in the middle of the shape? Well, it just depends on whether, notice up here the region is flush up against the line of rotation the whole way through. Notice down here the region does not touch the line of rotation except for at the very end. So that's why there's a hole when you start rotating it. Okay, so my integral is going to look like this. Pi, and I'm going to have some big R squared minus some small r squared, and then I'm going to have a little either dx or dy. So we look at this and say, okay, we just found out that it's a hole, so we're going to use the washer method. And notice that these things are stacking up horizontally, which means the thickness of the little shape is going to be along parallel to the x-axis. So that means that my height is going to be dx instead of dy. Notice in part B, the washers were stacking up, and so the little bit of thickness is in the y direction. Here, the washers are kind of side by side, or the discs are stacking up. Here, the washers are side by side, and so the thickness of those washers is just is parallel to the x-axis. So that's a dx. Okay. So now I just got to find the big R and little r. Now I'm going to erase all this so I can see it better, because when I start drawing all this stuff in here, it gets real fuzzy. Okay, so let's redraw this, and here's my. So I need to find a big R and a small r. Now notice the big R is from the line of rotation to the outside edge. Well, it's helpful to draw a few of these, so I'm going to get a different color, like red, and I'm going to draw 1, 2. Notice those are all big R's, right? From the inside, from the line of rotation to the outside edge. And notice they're the same all the time. So my big R in this case is set. It's not changing. It's always 1. So I'm going to put a 1 in there. Now my little r, get those guys out of there, and I'll grab a different color. Actually, that guy's too wide. There we go. So my little r is going to be from the line of rotation to the inside edge. So notice that guy's changing all the time. He's changing, and he depends upon that curve y equals x squared again. Okay, so I'm going to go and pick one of these points at random, write the coordinates of that point. So the coordinates of that point are x comma x squared, or square root of y comma y. Now in this case, I'm looking for a vertical distance, so I'm looking for the y coordinate. So that would be x squared or y. But I want it to be in terms of x because I have a dx here. So that means this would just be x squared. So I'm going to have pi times the integral of, and I'm integrating the same region, so it's still going to be from 0 to 1. Because notice this region, if you go from in the y direction, it's 0 from 1, but if you go in the x direction, it's also from 0. So that doesn't change no matter what I do. So this is going to be 1 minus x to the 4th whole thing times dx. Okay? I think I'll do one more example here. This guy's getting kind of long, and then I'll probably come back and just do a second video to finish this, or at least to get further into it. Yeah. Okay. So find the volume of the solid obtained by rotating r around the line y equals, or x equals -2. So let's draw I want to go back to my other color. So here's a line. Here's my region again. It's the same region, but this time I'm rotating around the line x equals -2. So that would be 1, 2. Here's my line of rotation out here. Wow, that was a horrible line. Line of rotation right there. Okay. So maybe you can picture it. It's spinning around the outside here, right? So, and here's the outside edge spinning around. That would be like the top of it. So it looks like a kind of a bowl with really thick edges. But I'm going to erase all that because it just clouds my vision. Because what I got from that is there's going to be a hole in the middle. And also I know that because the edge of the region is not touching the line of rotation. So that means my integral is going to be pi times some big R squared minus some small r squared. And it looks like it's running vertical. The line of rotation is vertical, so that means it's going to be stacking up vertical. So the little change in height is a dy again. So I'll put a dy out here, which means all of my stuff needs to be in terms of y. I can go ahead and put the 0 and 1 in now because I know it's going to be that. Okay. So now I'm going to draw some a big R and a little r. So I'll use green first. It looks like we've been using green for the little r. So notice the little r is, again, it's the distance from the line of rotation to the inside edge. And notice no matter where I draw it, it's the same length all the time. And that length is 2, right? So that means I'm going to put a 2 in there. And now you might be tempted to think it's -2 because that's at -2, but remember, we're talking about a length, a distance. How far is this edge from that edge? It doesn't matter whether you're never going to have a negative length, okay? So the distance is 2. It's 2. If you want to think about negative, you can say this distance is 0 minus a -2, right? Which would give you 2. I don't think we need to do it that way, but you could think of it that way if you wanted to. Okay. So that's the big R, the little r. Now we need to get the big R. I'll go back to red here. Red is pretty. Okay, and let's draw some examples of the big R. So there's, hey, it didn't change. What happened? I said red because it's pretty. Thank you. Okay, so here's an example of a big R. There's an example of a big R because I'm drawing from the line of the outside edge. Now notice that this encompasses that little 2 that we had there, but it also has this other little space here. So it looks like it's going to be maybe 2 plus something. So the question is, what is this little something that's growing all the time? So once again, we're going to go and pick one of these points on the curve, and we're going to say, well, we know that this thing is x comma x squared, or we can think of it as the square root of y comma y. How we describe those 2 points. And that's the same for any point. It doesn't matter where I pick. It would be true for all of these, right? So, and what we're interested in is the x-coordinate, because we want to know the horizontal distance, or the distance of the point from the y-axis, because that's what would represent these spots here, right? So I'm looking for either x or square root of y. Since I'm in dy, that means I want to grab the square root of y. So we're going to put the square root of y right there. And that would be my integral. So then I would simplify that and evaluate it. Okay, I think I'll do one more because this is so fun. Okay, in this case, once again, we have the same region. Find the volume of the solid obtained by rotating r around the line x equals 3. So x equals 3 would be over here somewhere. Remember, this is 1, 2, 3. So there's a dotted line representing my line of rotation. This is definitely going to have a big hole in the middle. You can see this big gaping hole because this edge of the region is not even close to the line of rotation. So we definitely need to do 0 to 1 again, from big R squared minus little r squared. And the question is it dy or dx? Well, since our line of rotation is vertical, and we're spinning around it, we're going to be stacking these things up, stacking up the washers. So the change in y, or the height is going to be a little change in y again. So we're going to put a dy out here. Okay? And we just need to find a big R and a little r. So let's grab our colored pens again. I'll just use red because it's ready. So that's big R. So notice big R is going to be that, or that, or that, etc. Looks like big R is the same all the time. And it's 3. So I'd put a 3 right there, because the outside edge of my region is at 0 and the line of rotation is at 3, so that's clearly going to be 3. And then the small r is examples right there and right there and right there. Okay, now this one's a little bit troublesome, because if I look at that point right there, like we've been doing, again, that point is, well, it's in terms of y, so I'm just going to use that one. This would be the square root of y, comma, y. So the y coordinate is y, and the x coordinate is the square root of y. So in other words, the horizontal distance, the distance from the y-axis is square root of y. The distance from the x-axis is y. So notice in this case, I really want this green distance here, which is not the x-coordinate. The x-coordinate is actually, let me draw a different, grab me a different color. Purple. This square root of y is represented by that distance right there. Do you buy that? So I need to get the green distance knowing the purple distance. But I also know the total distance, don't I? The total distance, of course, is 3. So to get that little green distance, which I want, I'm going to go 3 minus the square root of y. Because you can see if you take the whole distance of 3, subtract off the square root of y, it leaves you with that green. And notice that's true no matter which point I pick along here, because notice the purple is always the square root of y, and it gets smaller as we go down, which makes the green get longer. So I'm subtracting less than 3 and making my green go longer. Okay, well, there's some good examples of washer and disk method, both with the y's and the x's, rotating around a horizontal or a vertical axis. So that should help you make some headway in understanding this material. All right.